Okay, here we have section 6.3 on separation of variables and the logistic equation. So to find the general solution of a differential equation such as this, we need to get dy dx by itself, and we need to basically solve for y. But if I see that I have both variables here, there's something that we need to do called separation of variables, which means I need to get all the y's on the left side and all the x's on the right side, including the dx and dy. So I'm going to leave the dy there. I'm going to need to multiply the dx over, divide the x squared plus 4, and bring the y over. So all of those steps, I'm going to end up with dy over y equals x over x squared plus 4 dx. Now that I have everything separated, I take the integral of both sides separately. So on the left side, if I have a y on the bottom like that, it's going to be natural log y. And on the right side, that's going to be natural log as well. With u substitution, there'd be an extra 1/2 we have to remember. X squared plus 4 plus c. Now, in order to get rid of those natural logs, I need to move this 1/2 to be an exponent with the x squared plus 4. And then I can exponentiate both sides. So I have y equals, and with the c, remember when we take exponential, that becomes a c out front. And then we have e to the square root of x squared plus 4. Actually, sorry about that. The e, because the e cancels with the natural log, it's just going to be x squared plus 4, but the c does still stay at the front. Okay. Okay. Given the initial condition, 0, 1, find the particular solution of the equation, xy dx plus e to the negative x squared times y squared minus 1 dy equals 0. Same process, we want to get all of the dx's and x's on the right side, all of the y's and dy's on the left. So I'm going to start by just moving the um, xy dx over to the right with subtraction. And then I'm going to need to do the dividing. So I'm going to divide the y over to the left and divide the exponential to the right. And when I divide the exponential to the right, it becomes a positive exponent. Because if you're dividing by e to the negative x, it becomes e to the positive x on the right side. Okay, on the left, that can be split up if I see a single term on the bottom in the process of taking the integral both sides here. This would split up into y minus 1 over y dy. And the right side would be u substitution with that exponent. Then you'd have an extra 2 you'd have to keep out there. So that side's done. The left side is y squared over 2 minus natural log y. Now I have that initial condition to worry about, 0, 1. So I'm going to plug in 0, 1. To figure out what c is. And c is 1. So I'm okay with you keeping it just like this. I know a lot of questions, or if you see answers in the book, they might have tried to isolate the y better, but I really just want to see that you can solve for the c and take all the antiderivatives correctly. So I'm okay with that right there. Okay. Find the equation of the curve that passes through the point 1, 3 with a slope of y over x squared at any point. So as soon as they give us an equation for slope, that is my dy dx. And I'm going to have to separate everything, bring the y's over to the left, bring the x's over to the right. And once I isolate everything, I can take the antiderivatives of each side. Looks like we're going to have natural log. That's going to happen a lot, but don't get confused with the right side thinking that's natural log because we just raise the exponent by 1 and divide by that same number. Okay. I'm going to take or exponentiate both sides. Remember that c comes down front, and I can now plug in the 0.13 to figure out what that c is. And it looks like c, when rearranged, is going to be 3e. So now just to plug that back in, y equals 3e constant, so I'm going to put it in parentheses, times e to the negative 1 over x. Okay, one more, and this is the logistic equation that the section was referencing at the beginning, where we have a rate of change. In this case, it's for the number of coyotes in a population being directly proportional to 650 minus n of t, where t is the time of years. When t equals 0, the population is 300, so we have one condition here. When t is 2, population is increased to 500. Find the population when t equals 3. So this first statement, I'm going to highlight, it's important. The rate of change of the number of coyotes, so it's going to be a derivative, is directly proportional to 650 minus n of t. So the rate of change of n, dn dt, is directly proportional to some value k to 650 minus n. And all of this is with respect to t, where time is t in years. Okay, so now setting that up, honestly, was probably the hardest part because now we can do the separating of variables, getting the n's over on the left side and any t's on the right. We're going to keep the k over on the right since that's just a constant, and we will take the integral with respect to t on that right side there. So take the antiderivative of each side. We're going to have negative natural log absolute value of 650 minus n. That negative is there because if I did u substitution because of the negative n, we would have an extra negative. And then the right is kt plus c. So I'm going to get rid of that negative, and in doing so, it's going to change the signs on the right side, negative kt minus c, and I do that to exponentiate, right? So we're going to exponentiate here. I'm going to come up here where I have some room. I have 650 minus n equals e to the negative kt minus c. That c comes down, right? I'm going to subtract the 650. I'm trying to get n by itself. And divide by a negative. So we had a couple algebra steps here. And we need to plug in our initial condition, 0, 300, to figure out what c is. And when I solve for that, I'm going to get c equals 350. I'm so sorry that I ran out of room. I'm assuming you probably did too if you wrote just as big as I did. So this is going to be 650 minus 350 e to the negative kt. What am I still missing here? I need to know what the rate of decay is, the k, in order to solve for the population when t is 3. So I'm going to have to plug in my other initial condition of 500 to solve for k. Okay, since we are significantly out of room, I'm assuming you are too, since this is just a couple algebra steps, I'm going to get us down to e to the negative 2k equals 3/7. And when I solve that, k is approximately 0.4236. So plugging that back into the blue equation that we have here, and we're trying to find out when t is 3, so I'm going to plug both of those in at the same time to save us a line of writing. And 3, rounding to about 552 coyotes. Okay, and our homework is up here in our work. That is the end of chapter 6.